Okay, so my topic was general equilibrium and LeChatliers principle. So general equilibrium is just, the most story you can get is a definition of dynamic equilibrium, which is just when the rate of the forward and the reverse reactions are equal, and the ratio of products to reactants are constant, so nothing's changing. So Kc is just the equilibrium constant, and you find it using the concentrations of products divided by the concentration of reactants at equilibrium. If you find Kc using concentrations at any other time rather than equilibrium, you're not finding Kc, you're finding Q, which is not Kc. So here's an example. You have 2HI yields H2 and I2, and it's giving the concentrations of each one at equilibrium. In a separate problem, in order to make it harder, it could give you the initial concentrations and give you Kc, and then want you to find the final concentrations. So all you would do was use an icebox and the Kc expression to find it. So here's how you solve that one. You just do the concentration of H2 times the concentration of I2 divided by the concentration of Hi squared. And you need to make sure you square it because there's two of them. So that's your answer. And then Kp is basically the exact same thing, except for you're using the partial pressures of the gases versus the concentrations. So it's just the partial pressure of products divided by the partial pressure of reactants at equilibrium. Okay. So then here's the same problem, except for this time it's giving the partial pressures of each one at equilibrium. Like I said with the Kc one, it could give you initial partial pressures and want you to find the final partial pressures. So here's how you solve that one. I actually messed this one up. I forgot to square it. So you need to square this here because don't forget there's 2 of the Hi. So your answer would not be 0.100, it would be 0.222. So here's some graphs showing dynamic equilibrium. This is a forward reaction. You're starting with all reactants and no products, and you're ending with more products than you are reactants, which shows that the products are favored. And the green line down the middle just shows where equilibrium has been met. It's showing that the rate is equal. The rates of the forward and reverse reaction are equal, and then the concentrations of products and reactants are just constant. They're not equal, they're constant. So here's the same graph basically, except for this time your reactants are favored rather than your products being favored. And then this graph shows the reverse reaction where you're starting with all products and no reactants. And here you're ending with more reactants than you are products, which shows that the reactants here are favored. Same graph again, except for this time it's just showing that the products are favored. And actually this is not supposed to be reactants, it's supposed to be product. Okay. So the LeChatliers principle, it just says that when the factors that are governing equilibrium are changed, there's going to be some sort of shift in the system in order to reestablish the equilibrium position. So here's an example. If you have A plus B yields C and your delta H is positive, it's going to ask you what you would do to what the system would do in order to reestablish equilibrium if temperature were changed, if pressure were changed, if volume were changed, if a reactant was added, if a product was added, or if you added a catalyst. So if you add a catalyst, nothing would happen to the equilibrium because all a catalyst does is change the reaction pathway. It doesn't do anything to equilibrium position. So if you add a product, you'd be increasing the number of products, wanting to increase the number of reactants, so you'd shift to the left. If you increase the reactant, you increase all the reactants in general, so you'd want to increase the products too, so then you'd shift to the right. If you decreased the volume, you'd shift to the right. If you increase the pressure, you'd shift to the right. And if you decrease temperature, you'd shift to the left. So then here's Q. Q is basically the same thing as K, except for you're using concentrations at any given time. They don't have to be equilibrium concentrations. And all you do to find K is the same formula you use to define Q. So you do concentration of products over concentration of reactants. So then if Q is greater than K, then your reactants are going to be favored. If Q is less than K, then your products are favored. And if Q is equal to K, your equilibrium of the system is met. So here's delta G. Ms. Enlow told me I needed to let you guys know how delta G was related to K. And so it's just the formula negative RT ln of K. And I figured since Avery taught me how to remember it as rattling, I'd give her some credit right here. So your R is just 8.314 joules per mole K times temperature in kelvins times the natural log of the equilibrium constant to find delta G. So if you found delta G, if it was greater than 0 and your K was less than 1, then reactants would be favored. If the delta G was less than 0 and your K was greater than 1, then your products were favored. Whew. Okay, we're done. That's all I had. I want to let you guys know that I recorded this probably a good 50 times before I got this one. So, you're welcome.